we have Jacopo Jannone. Jacopo is a senior security engineer with a strong passion for reverse engineering that allows him to find issues on mobile, web, and native applications. His interest in identification systems such as smart card and RFID led him today to explain the risk carried by smart and POS. So, Jacopo, the stage is yours.
Thank you. Hi, everyone. Thank you for being here. OK, let's get straight into it. So I'm Jacopo. As they said, I am a penetration tester during the day. So basically, I like to break stuff. And that's what I do. But also, when I get out of work, that's also what I do. So this talk actually comes out of something I did for during the night, well, during several nights. And yeah, those are my contacts if you want to say hi. But yeah, before we begin, I want to spend a few words about the responsible disclosure process. The vulnerabilities I'm going to talk about here were responsibly disclosed to the vendor, and they are being addressed. As you might know, when you deal with payment stuff and payment companies, everything gets quite painful. It's still an ongoing process, not a closed matter yet. And for this reason, I will not disclose at this time the name of the affected device. I still believe that sharing this research right now is valuable, as it might be a wake-up call for other companies and regulators in the industry. And with that out of the way, let's get started. So up until a few years ago, this is how all credit card terminals looked like when you went to pay in any merchant. And these were basically custom hardware devices with a custom software stack. Basically, they had a very simple operating system that could only do one thing, and it did it pretty well. They had a pretty small attack surface. They didn't have very many interfaces. They had very basic internet connectivity. And so there was nothing really so much interesting to do there. While today, we are full of these things. And these are the so-called smart POS terminals. They are basically Android smartphones with still custom hardware. Of course, you have your thermal printer and card reader and so on. And the software is basically a custom Android build from the Android open source project. And it has all the customizations from the vendor. And then the payment application, of course, is a common Android application that is installed on top. Android, as a general purpose and a quite complex OS, has a much larger attack surface than your regular standard POS. And so, I mean, these devices also have USB ports. They have full internet access. They have file manager, complex bootloaders. And so I asked myself, is it really a good idea to have these devices process payments? And we're going to find out, although I guess you already know the answer if you're here. The first question is, where can I get one of those? And it turns out, if you go to eBay, you can find lots of them, like all kinds of POS terminals, and for very low prices too. And so guess what I did? I found a model that is very popular, especially here in Italy, but it's used pretty much worldwide. And the one I got was a brand new device, so it was still in the original box with the plastic wrap on it. It had a SIM card included. But I removed it as soon as I received it because these devices have like GPS. I didn't really want it to phone home and download updates and transmit who knows which analytics data from my network. So no internet for this device. But anyway, let's see how it looks. So after powering it up, I got straight to this first setup application. And it's not surprising that it complains that there is no SIM card in the device. Interestingly, this was actually the first setup application, so the media buttons were not working. I couldn't go to the home screen. The only thing I could do, basically, was pressing that service button. It's a service in Italian. And it would come up with a PIN request. So it was a numeric PIN, so only digits allowed. It did not have a limit in the code length. So I mean, I tried some pretty common combinations, such as 1, 2, 3, 4, 0, 0, 0, 0, but they didn't work. And so my first task was to get out of this application, or at least find the code and see where this service menu would lead. And so on the good side, there were no rate limits, so I could try as many codes as I wanted. I tried several of them. It didn't lock up, so yeah, I guess there was no limit. Still, without a fixed length, doing brute force, it's not something so easy. But you know, I remember I had a flipper 0 laying around. It has this useful bad USB function, which basically emulates a USB keyboard, and the device has a USB port, so that's very convenient. And so I thought, yeah, let's put them together, and this is what I did. So basically, I assumed that the pin code was 4 digits, and I started brute forcing the pin code using the flipper 0. That was the first thing that came to my mind. So the idea worked. In the end, it took like a whole day of trying to crack this code. It exhausted all the 4-digit combinations, and it didn't really find the correct one. So, I mean, the idea was cool, but it didn't work out. Maybe the pin code was actually longer, but trying with even only 5 digits would have taken like 2 weeks, and it wasn't really a time I wanted to wait for. And so, as I said, the POS was pretty popular. I spent quite some time with some savage OSINT online, looking for every video, every document I could find. And at one point, I found this YouTube video from a random Italian channel, and the video had like 7 views. But in the video, they showed the code, and so when I put it in, it went straight to the home screen. So this is pretty lame, because it would have been much cooler to say that the flipper 0 cracked the code, but real life is lame, so that's what it is. But anyway, the media keys also started working, which is useful. The media keys, by the way, are those to go to the home screen or go back or to the app switcher. And as you can see, there wasn't really so much interesting stuff. So there was basically just few stock Android applications. On the other page, there was like the payment application, but it was not configured because the POS was brand new. You know, it wasn't enrolled in a banking network, and so I couldn't do anything but like enrolling it. I couldn't do. It also had a custom app store, but yeah, it required login, it required network connectivity. So yeah, so on the plus side, I found a way home. I fixed the media buttons. I was free to play around in the OS, but there was nothing really useful to do in the OS. So I started brainstorming and thinking, what can I do with this thing? You know, you need to find an entry point if you want to do something interesting. Like you need to find it like a service to talk to, a way to install applications, a way to do something, right? And I thought there must be something. And one of the first things I thought of was ADB. So as you know, most Android smartphones have this option in the developer settings to turn on ADB, which is the debugging interface. And you usually go to the settings application, you go to the about this phone section, and you tap many times the build number until the developer settings unlock, which was not the case in this case. It didn't really work. So yeah, I stayed there tapping the build number for 1 hour. Didn't do anything. So, but anyway, in the security section of the settings, I found some evidence that maybe ADB was already enabled by default, because I found this option. I plugged the device to my computer, tried looking with the ADB client, but yeah, nope, no luck there. So next, I thought of, well, what about special boot modes? Most Android smartphones have special boot modes, so you can boot the device in bootloader mode, in fast boot, or in the recovery mode, and you usually do that by keeping pressed one of the volume buttons on the device while it boots. And I tried all possible combinations. The only one that did something mildly interesting was keeping both volume buttons pressed. And it basically went into this factory test mode, which allowed to test every single hardware feature of the device, so the microphone, camera, Bluetooth, Wi-Fi, GPS, and so on. And I figured this was basically a sort of custom recovery mode, but it wasn't really that useful. So once again, no attack surface, you know. And these are not the only things I tried. There are several other attempts that I won't go into the details, but I looked for the network surface, so looking for open network ports. I looked at the interfaces that the device exposed over USB. I found in the battery compartment some test points, and I thought, well, maybe they can give access to a serial console or maybe even a JTAG, but nope, nothing there. I did not try to disassemble the device because, as you might know, POS terminals have lots of tamper switches and sensors, and if you try to open it up, they basically erase the keys that allow them to work, and it would stop working, so I didn't want to do that. Although the FCC ID is always a useful source of information, so I looked it up in the FCC database to look for internal pictures, and that was something I could do. And another thing I did not do, as I said before, I didn't let the device connect to the internet, so I wanted to do a research completely offline. I didn't want to talk to some servers, and because also it was risky. I didn't have a waiver from the owner of the servers to do some pen tests on them, so I didn't do that. And at one point, actually, I couldn't think of anything else to try. So I started thinking that maybe I was wrong about the attack surface. Maybe Android terminals are not a bad idea after all, right? And at one point, my mood was like here. I was almost going to accept that I couldn't find anything. And so what did I do? I went back to Google and to YouTube looking for videos, looking for interesting stuff, right? And at one point, I see a YouTube short by some random technician, which had the same exact post as mine, and it said how to test the thermal printer. And I was like, okay, so he's going to show the factory test mode, so boring, nothing useful there. And instead, he does something that really puzzles me. He opens the calculator up, types in some keys, and the secret application opens. And I was like, no way, this won't work on my device, right? And so I tried on my device. I opened the calculator up. The key sequence was the factorial symbol, a super secret key combination, and the equal sign. And I couldn't believe that. So it worked. But anyway, this is just another diagnostic application. It allows to test each single component of the device. So it allows to test the Wi-Fi, the thermal printer, Bluetooth, and so on. So, okay. Although one thing caught my attention and was this COM option. And it really sounded like something serial port-ish looking. And going into that test, you can find this a whole bunch of options, among which there is one called shell transfer. And I was like, this is... So if you start it, this is how it looks. The device starts waiting for commands, whatever it means. And I figured maybe I should connect the POS to the computer and look if it exposed any serial port. And sure enough, it did. So I connected with a serial console. So this is the serial console open while that command is running. And I mean, nothing came out on the console. I thought, well, I should try to send some random stuff and see how it responds. Maybe it gives an error that may be useful to understand what this function does. And so, I just tried typing ping and sending ping to the device and looking for which error it would give. And this is not what I expected. I did expect some command injection in some functionality, but I did not think that there was like command execution by design. But okay, let's not get too excited. So let's try running another command to see which privilege we have, and we already have a system shell, so that's not bad at all. System is not root, so we will get to it later, but it's not bad as a start point from a debug application. First, before going in and continuing the exploration, I really wanted to have a true shell, because this is not a shell. This is command execution, so you don't have dollar variables, you don't have pipes, you cannot run interactive programs, you don't have file redirection. And so it was very annoying to run commands this way. And I thought, well, how do I turn this into a shell? And I thought the easiest way was Telnet. That's basically the easiest protocol I could think of. And also, BusyBox includes Telnet, which is useful. BusyBox is a collection of utilities you can find on Linux, and it's also very popular on Android devices for rooting Android devices. And so it was easy to find a precompiled BusyBox executable. And so the only thing I had to do was to turn the USB mode to NTP, which exposes the device, the internal storage on a computer. This is quite normal. I put the BusyBox binary in there. And then what I had to do was basically put the BusyBox binary in the data partition, because you cannot execute stuff from the SD card path. I changed the permission, and it works. So yeah, having BusyBox there, I could just start a telnet daemon like this, specifying a port and a command to execute. And at that point, basically, a telnet daemon starting in the background. As I said before, since I wanted to stay offline, I just created a custom Wi-Fi with no internet access. Or I also use sometimes the Android hotspot function, which was pretty useful. So the Android basically was the router, and I connected to that network. But anyway, so let's try connecting using a telnet client. And we put in the IP address and the port, and we're in. So this is a true shell, finally, and it's pretty good. But it's just the beginning, right? So we are system, we are not root. And so these are the things we can do with a system user. So we can enable or disable apps and services, which is useful. Some of them were annoying, continuing to start up automatically. I disabled them. You could extract part of the firmware and also system applications. And so I could start at least reverse engineering part of the stuff that was on the firmware. On the other hand, I didn't have access to the dev folder, which contains the device files. So I couldn't just take a full dump of the memory of the device. I couldn't disable SLinux, which is a security feature, which basically blocks you from doing something even if you're root. I couldn't play around with file systems, and I couldn't modify the system partition. And also, I didn't have persistency. So of course, every time I rebooted the device, I had to do all this thing from the beginning, right? Starting from the shell access. And so it's clear that if we want to do something more useful and more interesting, we need to find a way to escalate our privileges. And this is where the exploiting part of the talk basically begins. So I started looking for services running as root, looking for something useful. I extracted some of the services, started looking at them. And one that caught my attention was called POS tool. And it's this, basically this service, as I said, running as root. It was called POS tool server, the executable binary. But it caught my attention because there was also a client executable in the system bean directory. So it was basically a server-client architecture, not server in the sense of over the network, remote server, but on the device as a system service. Now, I didn't really know how to use the POS tool command, but this is what I figured out. So I got this idea that there was POS tool server, which was a demo running as root, and then a POS tool client, which communicated with the POS tool server via IPC. And so, you know, this is a pretty standard architecture, but it's pretty useful if you are looking for privilege escalation, right? So I started looking, I spin up my favorite decompiler and started looking at the two executables. I started with the main function of POS tool, which is, of course, where argument parsing happens, because I wanted to see how to use it, at least. And I figured that it had this, one of the commands it had was start, followed by two string arguments. And this is the function that parses that start command. It looks complex, but it's actually pretty simple. So it takes the two string arguments that follow the start command, and it uses them to build a shell command, and then it calls this function POS tool exec shell cmd. But crucially, this function doesn't actually execute the shell command. It sends it to POS tool server, which then executes the command as root, and so that's interesting, you know. And so we don't need to look at all this ugly stuff. This is the only line that my eyes saw when I saw this function. And I was like, okay, say no more, I know what to do. And so I opened my shell, and this is basically what I tried. I tried sending some simple command injection stuff like this. And trying to execute it, it didn't work. And so I went back to the code, and I said, okay, maybe I should not discard all the other parts of the function. And I noticed that here there was some basic deny listing. So yeah, I couldn't use the $ and other symbols, which, by the way, in my opinion, was a giveaway that somebody had already been there. But anyway, so those symbols are forbidden, okay. But not only that, in the client side of things, I also found that this code that basically checks for some condition, for some function, and if it returns 0, it denies the commands. And what does this function do? Well, it checks if the device is a debug unit. And so on my device, of course, was not a debug unit, it was a production device. So yeah, I thought, well, maybe I cannot use post tool because it looks for debug devices only. But then again, I thought, well, this code is in the client side of things. And so if it is in the post tool binary, I can take out the executable from the POS, I can patch it, put it back to the data partition, and execute it from there. And that way, I can bypass this check, right? And while I was at it, I said, well, since this part of the code is also in the client part of the executable, I might as well change it to just execute the two arguments that I pass in the command line. So I wouldn't have to bother with bypassing the deny list in the shell filtering stuff, right? And so that's exactly what I did. I patched the binary, put it back on the device, I called it post tool patched, and tried running this command. So in this case, it creates an empty file, which is more useful than who am I, since I really wanted to do it afterwards. I didn't have the output of the command. And it gave an OK. So I was pretty hopeful, but it didn't really work. So once again, no luck there. I looked at the logs this time to find what was wrong, and I found this line. So permission denied to execute that command. And first of all, this was nice to see because it was actually trying to execute that command, so it was good news. But it didn't work. And so I went back to once again, to our function that I should have looked much better at the beginning. And at the start, there is this other check, is exec shell cmd granite. And if it is 0, it returns this permission denied error. So that's exactly the error I found in the logs. And so what does this function do? Well, basically, it checks if the client process name is either post tool or system bin post tool or system server. Basically, they check the client process name to authenticate the client to the server. But that's not how you do it. I mean, you should specify at least always the full absolute path. You know, if you don't specify the absolute path, you can just rename any executable in any part of the system and it would work. And so I renamed my post tool patch to post tool. I added the current directory to the path, so I didn't have to specify the current directory when launching the executable. I tried again with my touch command, and this time it worked. It created a file as root. And so now the only thing, thank you. Yeah. And so now the only thing I had to do was to spawn a shell the same way as I did before in the serial console. And after connecting to a new telnet shell on another port, since this telnet daemon would run as root, I would have a root shell. And this is what I got. So now I got root. So what can I do that I couldn't do before? Well, accessing raw devices, no problem now. So I could take a full dump of the file system and also some interesting parts, such as the bootloader. I could disable SV Linux, which was annoying. I could play around with file systems, although I still did not have persistence. So once again, after rebooting the device, I had to do everything from scratch. And still, modifying the system partition was not possible. In fact, you must keep in mind that although we have a root shell, the bootloader is still locked. And so we have, of course, the root file system is read-only because it's from a RAM disk, so we can do nothing about that. But the system partition is read-only because there is the mVerity, which is this Android security features, which basically signs the system partition, and if the signature is broken, the device won't boot anymore. And so those two partitions, we cannot write to them. We can write to the data partition, of course, and also to the cache partition, although that's usually pretty useless. The natural question here might be, can we unlock the bootloader? And the short answer is probably yes. But for this presentation, for this time, we're not going to do it because there's need for more work and more research there. And I decided to do everything with the bootloader locked. So moving on, I took a dump of the whole system and started exploring it, right? So I put special attention on the system binaries that I didn't have the permission to read before. And interestingly, there were also some shell scripts in the system bin directory. And the second one was was also pretty interesting. It had a bunch of functions which are apparently executed during boot. And these functions basically prepare the device with some personalizations, some fonts and libraries from the customer. And the customer here is actually the acquirer, so the company that provides you this POS terminal. So let's take a look at the last function, customer init, which is the most interesting one. It also had a nice comment for future use, okay? And it says, execute customer init.sh if it exists. And I mean, looking at the line below, I can see that it checks if this file exists in the cache partition. But we can write to the cache partition, right? And so, yeah, I thought, well, maybe if I want to have the persistence, I can just create this file that there was not there. So at that path, there was no file. I decided to create it and to see what happens. And so I created a script. The first instruction, the first command I put in there was to disable SE-Linux, and then the command to just execute the my telnet shell, right? And so let's see how it works if by rebooting the device. So here the device is booting, and it's still starting up. Yeah, we need to wait a few seconds until it connects to Wi-Fi, and then we can try to connect to the telnet shell. It's a bit slow, but it will happen, I promise. And there it is. And we are in. And so now we have an automatic root shell at boot on a production POS that is still capable of processing transaction, which is quite cool and a bit scary, if you ask me. Now, I want to take a quick tangent about app installation because it's interesting and fun. Now, on these kind of devices, you cannot just install any application because differently from normal Android devices, the signature of any application you install must be from the manufacturer itself. While on normal Android devices, you can install applications which are signed by any developer, right? And so trying to install any application wouldn't work. And the way that this check was performed was pretty interesting. So as it turns out, the verification was performed by a system service, which was written in Java, so pretty easy to decompile using JADEX. And it calculates the hash, the SHA-256 hash of the app you want to install. And then it encrypts the hash. And here I want to stop a bit. How does it encrypt the hash? It does so using a key from the secure processor. And the secure processor is a separate processor that is in this kind of devices, and it handles all the security stuff. And so this key, which encrypts the hash, we cannot take it out. I mean, unless that's a whole another story, looking at the security of the secure processor, right? And so I assume that we will not be able to get this key. We need to find a way around this. And anyway, after the hash is encrypted, it is checked in an allow list, which is basically a SQLite database. And so I figured that to install arbitrary application on this thing, I had to calculate the hash, encrypt the hash, and then put the hash on the database. But since I did not have the key to encrypt the hash, I couldn't do it. Although, wait a moment, what is this? This is like a log function that logs the encrypted hash before checking if the app is allowed or not. And this is quite useful also. The log function only works if this debug security variable is set, but if we go look where it is taken from, it is just taken from a system property, which we can modify since we have a root shell, right? And so that's what I did. I just changed that property to make it look like it was I don't know, debug. It increased the logging anyway, and so after trying to install an arbitrary application, it logged the encrypted hash. So that's the correct hash that must be in the allow list. And so I just inserted the hash in the SQLite database using. I didn't even have to take the database out of the device because they had this SQLite free tool. So. Yeah, and I could install. So this is how I was able to install arbitrary application. Not really useful for what we want to do, but I think it was cool, and it fulfills the mandatory. Yeah, but let's go back to seriousness for a moment. I mean, we want to steal payment information. That's why you're here, right? And so I encountered a problem because on my POS, I couldn't actually process payments or even simulate payments because it was, as I said, it was a new device. It wasn't enrolled in a bank network. And so it didn't have a contract associated with it. In the payment application, I couldn't even type the amount because it wanted to perform the first setup. And so the easiest thing I could think of to solve this problem was to buy another POS and maybe flag the used option on eBay to make sure that it was used, not brand new, and hope that it wouldn't be factory reset. And so that's what I did on the Christmas day in 2023. For $10, I bought the device, and luckily enough, it was still enrolled in the banking contract of the previous owner. And so I could open the payment application, type an amount, and process payments. They wouldn't go through because it was offline, but still. This application became, of course, my primary target. Now, I won't go into the details of how smart card and the EMV transaction works, but the idea is that for each information that the POS must take from a card, the POS sends a read record command to the card, and the card responds with a bunch of data that the POS then decodes it and uses it to do its thing, you know? So if the goal is to capture credit card data, capturing the card responses is what we want, right? And in a payment application, there was this useful function, env get TLV data, which basically does exactly that. So basically, this function takes a tag, which is a record ID, and then it returns the result already decoded as a byte array in the result argument, which is just a pointer to say. So that was the perfect candidate to hook onto with Frida. For those who don't know, Frida is a dynamic instrumentation tool that you can use to inject code into functions at runtime. And so that's what I did. So this is the script I wrote. It hooks the function that we saw before, so env get TLV data. And this way, it basically captures all messages that from the card are sent back to the POS. So all of the rest of the script is just pretty printing to make it cool for this demo. And so let's see it in action. So here I'm typing the amount. I'm taking this is a prepaid card with no money in it, so don't add it to your Amazon account. Thank you very much. But anyway, I put it into the device, and as soon as we put it in, we get all the card data. And this is cool. So we get the card type, the card number. We would also get the cardholder name, but this card was an anonymous card, so no cardholder name here. The expiration date, and also the magnetic stripe stuff that is written on the magnetic stripe, because that's also present in the electronic part of the card. So that's also nice. Now, what about the PIN code? So for the PIN code, we need to make a separate discussion. Because, of course, the POS cannot read the PIN code from the card. There is no command that allows the POS to read a PIN from the credit card. And how it works is that the user types the PIN, and the POS sends the PIN to the card, and the card responds with OK or wrong PIN, you know? So if we want to intercept the PIN, we must intercept it directly from user inputs, from when the user types it. And this is not that easy, because there is this architecture where during PIN entry, basically the touch panel directly talks to the secure processor, and Android is completely cut out of this process. So when you are in the screen with the keypad to enter the PIN, the rest of the touch screen doesn't actually work. And then, as you can see in the video there, any part of the screen I touch that is not the keypad doesn't really work. The kernel, the Android kernel, does not receive the hardware interrupts from the touch panel. So that's pretty good isolation. It's almost basically physically isolated, right? And so what happens is that you type the PIN goes to the secure processor, and then the secure processor talks directly to the card. So there is no, Android is completely uninvolved in this process, right? And so in principle, this means that from my level of access, from being root on Android, still I wouldn't be able to intercept the pin unless I broke the secure processor. Although, actually, let's see how the application processes payment. So this is the pin verification function from that payment application that you saw before. And as you can see, it's a very simple function and short function, because all it does is call this verify pin function. And this second function is from the vendor SDK. Of course, the developers of the payment application just include in their application the SDK from the hardware vendor, and that's the SDK is the thing that has all the functions to perform the pin verification and so on, right? And so this is how it works. But the SDK actually has quite a lot of those functions, like several functions for verifying the pin code in several different ways, used in different scenarios, and not even all of them were used by the payment application, but they were there, right? And it turns out there's this function which only requests the pin and returns it to Android in encrypted form. And this is interesting because at least we are receiving an encrypted form of the pin, but we are still receiving something that looks like the pin on the Android side, although it's encrypted. How is it encrypted? Well, it's encrypted using triple DES, so no big, I mean, it's pretty normal in payment stuff. But the key that was used for encryption was the key that was basically enrolled in the terminal when it was first enabled in the banking contract, right? So when you do the enrollment process, the terminal basically downloads the key and stores it in the secure processor for this kind of operation. And interestingly, there was also a function that allowed to write a custom key to the secure processor, and I think you see where this is going. By the way, you should know that the secure processor has a number of slots, so each slot can contain a key. And if we can write a custom key to one of those unused slots, then maybe we can just encrypt the pin with that key we chose and then decrypt it, right? And so the plan was to do all of this in Frida, intercept calls to this perform pin verification function, and when the function is called, actually call this write key function that would write a custom key in an unused slot of the terminal. Then call the get encrypted pin, passing in the slot so that the pin would be encrypted with that key, and then decrypt the pin using the custom key, right? So putting it all together, this is the script I came up with. We hooked the perform pin verification function. We define a custom DES encryption key, which is this byte array. We also need to specify a card number because the pin, for some reason, before being encrypted is XORed with the card number. You know. And then, of course, we can call this write key function, passing in all the required information. So in particular, we pass the key slot that we're going to use, that is the number 2. And then, so we call the function, sorry. We prepare, we pass in the byte array with the decryption key, and then next we call the get encrypted pin function. So once again, we specify the slot number for the key that must be used for encrypting the pin, which is slot number 2, and a whole bunch of other stuff that it needs, such as the card PAN that you saw before. And so the result of this get encrypted pin function will be directly the encrypted pin. So we take it out, we take it into a byte array. We also prepare an array for the decryption key. And then, since I didn't want to implement triple DES in JavaScript, it would be much painful, I decided to just leverage the decryption function that was included in the SDK, right? So this is a native function. This is the function basically from the shared library. You need to pass in the signature so that Frida works. This is an array for the result that I prepared for receiving the result of the decryption process. And then I call the decryption function, passing in the encrypted pin, the result buffer, the encryption key, and a whole other, like the length of stuff, and a 0. I don't know what it means. But anyway, then I had to just take the result of this function, read the decrypted pin, and then I had to perform the XOR with the card number just to unwrap the stuff. And the rest of the, I had to take out the actual pin length, so the length of the pin, and then the rest of the stuff is just performing the XOR and pretty printing for seeing the pin in human readable form. And so I think that's enough talking. Let's see it in action. So once again, we have our payment application. We are typing the amount. We insert the credit card. We get all of the data as before, and we type the PIN, 5297. And there we have it. So now we have a weaponized POS terminal, which looks and feels perfectly normal. This is the standard payment application, and the PIN prompt also still happens in that secure way. You know, it's handled by the secure processor. So if you touch other part of the screen, it won't work, and so on. And so it really feels like, I mean, there's no way of detecting that something weird is going on, right? And also, notice that all of this is done wirelessly. There's no wires connected to the device. And so you can even do it at, in the restaurants where the waiter comes to the table. But anyway, yeah. So that's basically it. And I have some takeaways out of this research. If you have features that involve arbitrary command execution, maybe make sure they don't end up in production. In the case of POS tool, put all the security features in the system service, not in the client. Also, if you not check if a process is legit, make sure you look for the absolute path. Do not trust modifiable system properties. That's how I enable that debug flag to increase logging and log the application hash. Do not log sensitive data. That's like security 101. Do not execute stuff, especially as root, from writable partitions. And also, each feature you add to the SDK, even if you don't use it, is a feature I can exploit, right? So despite this research being quite long, there is still so much left to explore. So I have here a list of interesting things that maybe I could go through in the future, or maybe somebody else, like playing with the bootloader, analyzing network traffic, having a better look at the secure processor, looking for unusual attack vectors. I thought of maybe what if we use a malicious credit card? That's also an interesting scenario to explore, right? Disassemble the device and play with the hardware. I could do it now that I have two terminals. And then, you know, what about other POS brands? As a small spoiler, I already have bought several other POS terminals, and so yeah, so this is the end, but just for now. Thank you.